This question says, let I be an ideal in a commutative ring R with unity. Show that I is a free R module if and only if there is a non-zero divisor A in R with I equal to RA. Okay, so let's do the forward direction first. So first, suppose I, our ideal, is a free R module. Well, what it means to be a free R module is that I has a basis. So then I has a basis. And we want to show that I is equal to RA. Um, so uh, what we're going to do is we're going to show that I cannot have two distinct elements in its basis. So suppose for contradiction, I1 and I2 um, elements of I were two distinct elements of a basis for I. Well, then we have a relation. We have in particular that I2 times I1 and then plus minus I1 times I2. That's equal to 0, even though I1 and I2 can't both be 0. There's only one 0. So even though I2 and negative I1 are not both 0, so this means that I1 and I2 is not a linearly independent set, contradicting that they belong to a basis for I. So what have we learned? Well, the basis for I, which we know exists since I is a free R module by assumption in this direction, um, so the basis for I can have only one element, and we'll call that A in I. Okay, since the set containing A is a basis, then by the definition, that's every element in I can be written uniquely in the form RA for some R in R. And what does that tell us? That tells us that I is a subset of RA. But also I is an ideal and A is an element of I, so R has to absorb products from R. So RA is a subset of I. So I is equal to RA. Also, that's most of what we need, but we also need to say that A is not a zero divisor. Well, if A were a zero divisor, then there would exist some B in R such that B times A equals zero. Definition of a zero divisor just means there exists some B in R such that either BA equals zero or AB equals zero, but since we're in a commutative ring, it's equivalent, so we can just say that there exists a B such that BA is equal to zero. Um, but sorry, there exists a B non-zero. B is not zero. Um, but this would contradict set containing A being a linearly independent set. In particular, we've written as zero as a linear combination of elements of our uh, set where the scalars are not all zero. Okay, so set containing A is not linearly independent and that's not a basis. So uh, that would be a contradiction. So A cannot be a zero divisor. Okay, so that completes that direction of the proof. For the other direction, so let I be an ideal as before, and suppose I is equal to RA for some non-zero divisor A in R. Well, to show I is a free R module, will show I is isomorphic to R as R modules, which implies the result because R is a free R module over itself. Or rather, R is a free R module. Uh, the basis, as it has the basis consisting of just the element one, right? Every element in R can be written uniquely as R times one for some R in R. Um, so indeed, R is a free R module. So if we can show that I is isomorphic to R as R modules, then I will also have to be a free R module, which is what we want. So, okay, let's exhibit the R module isomorphism. Define the map phi from R to I by phi sends R to R times A, where A is our element. We have A is our non-zero divisor, A and R, such that I is equal to RA. Um, Now, since I is equal to RA, what we get, phi is spitting out something in I, uh, so this is well defined. So now we have to show that phi is an R module isomorphism, and to do that, we have to show that it's an R module homomorphism and that it's a bijection. Let's check that it's an R module homomorphism. So if we have two elements R1 and R2 in R, then phi of R1 plus R2 is R1 plus R2 times A, which is R1A plus R2A. Everything's living in the ring, so we can use the distributive law, and that is phi of R1 plus phi of R2. Okay, so that condition is checked. Uh, Now let R be an R and S be an R. Um, well, what's R phi of S? That's R times SA, which, oops, is the same as RS times A, which is phi of RS. Okay, so phi is indeed an R module homomorphism. Let's check that it's a bijection. Now suppose phi of R1 is equal to phi of R2. Well, then by definition of phi, R1A equals R2A. Now, we don't necessarily have a inverse for A, because A is not necessarily a unit, but we do know um, that we can subtract. So R1A minus R2A equals 0. And now we can do some factorization. So R1 minus R2 times A is equal to 0 by the distributive law. Since A is not a zero divisor, this means that R1 minus R2 must be 0, so R1 equals R2, and that says that phi is injective. Now, to show surjective, let I be an I. Since I is equal to RA, I is equal to little I is equal to little RA for some R and R. So phi of R is equal to RA, which is equal to I. So phi is surjective. Um, and therefore I is isomorphic to R as R modules, and thus, since R is a free R module, I is a free R module. Uh, Note that necessarily our A will have to be an I, since R is a ring with unity, and we're sending, it'll send 1 to um, A, and A should be the basis for I as well.